yeah, so um, whoops, that's not what I wanted. We want to hit this button. Okay. Excuse me. So, yes, welcome. It is good to have you virtually here. Yeah, a few things I want to just cover and talk about before we jump into Chapter 6 material for today. It's good to have you back. I know you weren't really gone because you were working on an exam, but we haven't been, we had Monday off in terms of lecture. I know a lot of you put in a lot of work on Monday. Yeah. So I've just started to comb through your exams, and just to reiterate a few points, as I mentioned, way back at the start of the semester, the way I go about grading exams, it's rather time consuming. So I read through kind of a lot of pretty much everything people have written to get a sense for how the questions were understood by you, largely. And so before I start assigning point totals and things like that, I want to get a feel for it. So it does take me some time to get through them all. So they won't be back tomorrow or something. But hopefully by the end of the weekend, I've had enough time to churn through those. Other things to keep in mind, and I know I've said this a few times, but some of these questions are difficult. Statistics is difficult on in some, and so it's not always going to be simple, straightforward questions. So if there were things that made you struggle, know that that's okay and somewhat expected, and I don't expect perfection. And I also want to point out that, and maybe we should have talked about this beforehand, but for a number of you, some of you may be upperclassmen, but a healthy number of you are freshmen, and you're now in the fall of your freshman year in this odd time. But also, these couple weeks here, you probably are having midterms in a number of your courses, and this is probably a pretty harsh transition from, to generalize. You probably did quite well on exams and tests in high school, and largely those are often, you might get 98 out of 100 on an exam, and that might not feel that unique in high school. This is kind of an abrupt transition to college course exams where the average outcome is not always a high percentage, and it varies by course, but a lot of courses you'll come across may have more of that. It's okay to get a few more things wrong than you did in high school, is what I'm trying to say, and that's a stressful transition. So I just want you to know that that's typical, so a couple other things. This is one exam, right? So it's not your whole grade. So if you did feel overwhelmed, know that we have a lot of semester left, and we can keep working on this stuff. Again, statistics it's a learning process. Very few people absorb everything right away. And so as we go through the course, a lot of the stuff that we've covered is going to keep coming up, and hopefully it'll sink in deeper as we go. So if you're feeling like, I can't understand this, it's not sinking in, we got more chances at it, and we'll keep working on it. To that end, if you are feeling stressed, or if you're feeling like maybe we need to devote some more time, know that so office hours are available, and again, as freshmen, for those of you that might be a new scenario as well, the meeting and taking advantage of those types of office hours. So please do utilize that. Again, you can find them on the syllabus, but the scheduled office hours are Wednesday and Friday, so later today and then Friday. Let me not mess up these times. 1:30 to 2:30. And if those times don't work, please reach out to me and we can find a time to meet that's not those. But that's a helpful way for you to ask, questions, more clarifying questions. And yeah, so not just in this class, but please, getting in the habit of taking advantage of those types of resources is good. I'm sure there's other things that I want to say. Oh, so what can you expect from me as far as the exams go? So now the digital version of it, a lot of you sent in PDFs or whatnot. I won't be marking up directly on your exams like I would if I had the paper copy. But what I'll present to you either in an email or if I can figure out how to do it well on Canvas, you'll get kind of a per question score. So I'll let you know, like, you got 8 out of the however many 11 points on question 2. Or I don't know what the questions were worth, but I'll give you kind of the breakdown per question. And then some form of kind of a solutions key, so you can look through and see, okay, I got some points off here. What was I supposed to do? Or what was a good way to go about it? Yeah, so that'll give you kind of a starting point is to understanding the exam. I'll also, once I'm through grading the exams, I'll have a better feel as to some of the concepts that maybe we need to just brush up on. So for instance, if, it turns out a lot of people were struggling with how to calculate a median, I'll make sure to take a little time in one of these, probably next week at some point in lecture, and just kind of, rehash how I think maybe the miscommunication or the missteps were happening most often. So if there's any big concepts like that, we'll make sure to cover them. Yeah, and then of course, as I mentioned at the start of the class semester, this is a good kind of time to finally give you some deeper insight. Now that we've taken an exam and you'll have a grade for an exam, I'll do my best to kind of outline what those results mean, right? So again, it's not based off of you got 82%, so that falls you exactly in this window, and so it won't be until after I'm done with this exam that I can give you a better sense as to you got 37 out of so many points, so that falls in this window of from 36 to 38, it's roughly equivalent to a certain grade. So I'll try to outline that better and give you a sense as to where you are in the class. Yeah. So, yeah. So if you have any questions, and either now or when you get the exams back or whatnot, again, reach out to me, or we can meet up in office hours or something and talk through some of that. So statistics is a busy subject, so we don't have a lot of time to sit and dwell on the past, and we're kind of forced to continue on if we want to get through all of the important things later on. So we're jumping right back in chapter 6. Chapter 6 is not I would say it's a little smaller, which is nice. It fits well here, but there's some complicated math, especially at the later end of the chapter. So I think the Connect assignment, which is posted, it only has 10 questions. Some of those are not going to be too cumbersome, but I would anticipate a few of them towards the end to take you some time, especially if we're going to rely, excuse me, we're going to rely on the combinations formula from chapter 5. So if that was a little confusing, it's going to take you some time to get through some of those questions in chapter 6. So just be heads up on that even though it says 10 questions, some of them might take you a bit. Okay. So today, I want to give a little bit of a framework as to where we are, what we're doing in these next few chapters, and kind of we're going to start a little basic today in terms of chapter 6. Now, somewhat because in a normal week I kind of expect by Wednesday that you're into the chapter a little bit, and you've either read or skimmed some of the chapter, or maybe started to work in Connect or something. You're making yourself um, aware of what's happening. I have a different expectation of you this week, knowing that you just racked your brains on an exam. Maybe some of you have started, but the likelihood is probably low that you're really into the nuts and bolts of it. So I want to spend more time today than we typically would, kind of framing the chapter and starting with some of the basic core concepts. And then on Friday, we'll spend more time walking through some examples and really touching on the later some of those specific binomial distributions and whatnot. So that's kind of our goal. So with that in mind, chapter 6 and chapter 7 are a pair of chapters. They go together. We're trying to do the same thing in both of those chapters. So as next week when we're in chapter 7, it might even clear up some of what we're trying to accomplish in chapter 6. So bear that in mind as we kind of jump into this. And in fact, at a certain point in chapter 6, you're introduced to the main difference between 6 and 7, and that comes down to what type of a variable we're talking about. Yeah, so the big transition we've been making, right? We're moving away from data that we've collected in chapters 1 through 4. We've moved into probabilities and trying to talk about likelihoods of events happening or outcomes occurring in the future, right? And so what we're trying to do is kind of build some models that allow us to predict what might happen or what the likelihood of a certain outcome happening. But we still have these kind of differences in what the scenario is or what the variable is that we're interested in. And so specifically, the difference between chapter 6 and chapter 7 is all about whether the variable we're talking about or the outcomes are discrete or continuous. Okay, so we're talking about random variables in both, and we'll talk about what that specifically means. But the big difference here is in chapter 6, we're talking about outcomes that are going to be kind of set amounts or fixed, very specific amounts. So in many cases, it ends up being an integer. So we're counting up something. We're counting up how many credit cards somebody has in their wallet or how many slices of pizza somebody ate. And it's either, 2, 3, 4. It's some value. Now, it doesn't have to be an integer. So we could think about, how many cups of flour are in this recipe. And it could be, it's either a quarter, a third, a half, a full cup. But they're defined values, and they're very specifically defined, and we know what all of those defined values are. And so that's a discrete variable rather than a continuous. Okay, so the discrete is right on some certain values that we know. The continuous can be anywhere along. So think of it more as how much rain did we get yesterday, and it can range. It could be 1 inch, it could be 2 inches, but it could really actually be 1.37 or 1.6243 inches, right? We could have the exact amount be anywhere along the number line. So the concept of what we want to do in chapter 6 and 7 isn't any different. Where this splits apart is what we can do mathematically. Okay, and so our goals in chapter 6 and 7 are the same, but the math is going to change. So what are our goals? Well, just like in chapters 1 through 4, what were we generally trying to do? We were trying to summarize the data, right? We collected data from something, right? Or we had data on Titanic survivors or Titanic passengers, because not all survived. So we had data on all of this, and we could look at who survived, who died, who was first class, second class, third class, all that type of stuff. We could summarize that. Okay. Here, we no longer have the data of what has occurred, but we have information or we're building a description of what might occur or how likely certain events are or outcomes are. We still want to summarize that. So in chapters 1 through 4, what did we do? We visualized it. We did so we did things like bar charts and histograms. right? And how did we build those? We built frequency tables or relative frequency tables. And then from that, we were able to build a bar chart or a histogram. Okay, other things we did were to summarize it numerically, and we said, here's the mean of this variable. Okay, the average age was, I don't know what it was, 27 years. Okay, we summarized by the mean. We also summarized using the standard deviation, right? How spread out was this variable? We did some other things, right? Median, range, all those types of things. But we spent a lot of time on mean and standard deviation. So we summarized in a frequency table or a relative frequency table, mean, standard deviation, and we visualized it with kind of a bar chart, where that was one option. So turning here, we've got likelihoods of events happening. Okay, so we've shifted gears, but we're still going to try to summarize that, and we're going to say, okay, we can build what is essentially a relative frequency table. You're gonna recognize it. We're gonna call it a probability distribution, but it's essentially the same process, or we end up with a very similar result. So we're gonna build that to try to summarize all these likelihoods that might occur. We are going to visualize it. Okay, if we have a relative frequency table, we can just plot that on a graph, and it basically becomes a bar chart. And so we'll do that as well. And then also numerically, we will spend time learning how to take the mean of these probability distributions and the standard deviation or the variance, right? So we'll do the same process of summarizing the data. Now, when we do the mean and the standard deviation, it's going to basically mimic what we did. One of the kind of unique ways of doing the mean and the standard deviation was when we talked about grouped data, and we changed our formulas a little bit to just make our lives a little easier. Okay, so the formula wasn't exactly the sum of x over n. We instead went about it slightly differently, and we'll do a very similar thing here. So we'll spend some time talking about probably in a separate video. I don't think we'll quite do it today, but that the process is a little different, but with something we've done before. So that's the overall goal here, is to summarize these distributions of possible outcomes, both in chapter 6 and 7. And again, the math is going to change when we get into continuous variables. We can't do quite the same things that we could do in chapter 6, and in vice versa, we can't do some of the things in chapter 6 that we're going to do in chapter 7. It doesn't flow, or it's not mathematically possible to do everything depending on the variable. So much like in chapter 1, we were very particular about, is this qualitative or quantitative? Here we have to be very particular if we have a discrete or a continuous variable. So that's much of what we do in chapter 6. Towards the end of chapter 6, we have a couple kind of specific scenarios, and we'll talk more about why we focus in on those. So there's binomial, there's hyper geometric, and then as I point out, so on Canvas you can see, I've indicated you can skip Poisson distribution. It's the last, I don't know, 3 or 4 pages. It's a useful tool, but it's a very specific application, and so we won't, for the sake of time, we won't devote time to it here. But if you're thumbing through and you want to read it and ask me questions, feel free to do that, and especially at office hours, if you want to chat more about it, we can walk through it as well. But if you're trying to get through the material and what you need to know, you can skip that section. Okay, so that's a lot of me just discussing what we're trying to do. So we'll kind of rewind here and talk a little bit more specifically. What is even this probability distribution that I've been going on and on about? All right, so let me pull up, and I'm going to just pull up some slides here, which we don't typically spend a lot of time in the slides, but I think that this is a good, I'll get out of the way too. It'll be a good framework to get us up and running with some of these concepts. So if I can click the buttons in the right order, we'll get this going. Okay, so probability distributions. We jumped in right away here, and I started talking about the difference between 6 and 7 and probability distributions, but what the heck was I talking about? Okay, so a probability distribution is more than just a one single probability. So we've, up until now, and in chapter 5, we spent some time thinking about what does it mean, what does a probability mean? What is a likelihood of some outcome happening? The probability distribution is simply we're listing out all of the outcomes of an experiment, and we're putting the probability associated with each outcome. So, for instance, one of the examples in chapter 5 we talked about was, the probability of Slowpoke, the horse, winning the Kentucky Derby. I'd update that, but I did not pay attention to the Preakness or whatever else, whichever one was run this past weekend or whenever that happened. Time has lost meaning, and I don't know. Horses are running in the fall. So, but if we think that there's an outcome where Slowpoke wins, and I think we said 0.2. So there's a 20% chance that Slowpoke wins. That in and of itself is not a probability distribution. We need to include all of the possible outcomes. So that would be, fast poke has a certain probability, slow jab, Secretariat's 5th grandson comes back. All of those horses that are running would have a chance to win the Derby. So we need to list all of those for it to be a probability distribution. So what are the characteristics of a probability distribution? Well, each probability, so each particular outcome, is between 0 and 1. They're all valid outcomes and valid probabilities, right? And recalling back to chapter 5, those probabilities are between 0 and 1 inclusive. You could have a 0% chance. If it really was Slowpoke, it might be close to 0. But all of the possible outcomes are listed. They're all between 0 and 1. They're all mutually exclusive. Okay, so we did talk on in chapter 5 that we could have various outcomes. Say I roll a die and I'm interested in a 2. I could also be interested in an even number coming up. Those are valid outcomes. But if we want to talk about a probability distribution, we can't have both of those in there. Because if you do roll a 2, you've satisfied both of them. Okay, and so we can't have that. We need our probabilities or our outcomes to be mutually exclusive. We also need them to be exhaustive, right? Collectively exhaustive, going back to that concept. So mutually exclusive and collectively exhaustive, those two concepts need to be satisfied here. What that means is then, if we're exhaustive, that means we've covered all of the possible outcomes. So the sum of those probabilities is equal to 1. We didn't leave one of the horses off, right? We didn't forget to put in Secretariat the 12th. If we had, then whatever chance that horse had wouldn't be in our list, and our sum wouldn't equal 1. Okay, so let's walk through a quick example. And this is, I think it's in your book. So we'll just kind of talk through it quickly because you can rehash it there as well. But it's a good way to introduce the process of getting to the probability distribution. So in this example, our experiment is we're going to flip a coin 3 times. Okay, and we have various results that could occur. We also have outcomes that we're interested in. And our outcomes in our case here, if we don't care, so notice we don't care about the order. Our outcomes here are just 0 heads, 1 head, 2 heads, or 3 heads. And so that's important we want to be very specific about what outcomes we're interested in. So note already from chapter 5, we should be able to count the number of results we can have. So we have 3 coins, each of them with 2 possible results. So we are able to calculate the number of results not necessarily yet the number of outcomes, and we'll talk about why that is in a second. But from chapter 5, we have 2 times 2 times 2, so we know that we have 8 results that could occur. Right? The first coin being a heads, then a tails and a tails. We could have heads, tails, heads. We could have tails, heads, tails, and so on. Right? And there's 8 different orders in which that could happen, or 8 different results. So listing those all out, and we can do that because it's not that many, we can kind of lay out what's possible here. So we have 8 different results. We have them all listed here, but notice the number of heads, the outcomes that we're interested in, and which hand is okay. So number of heads 0. There's only one way to do that, right? If we look down the list of possible results, we only have one that results in 1 head. When we get to result 2, we have 1 head, but that also could occur in multiple different ways, right? And it turns out there's 3 different results that lead us to the same outcome. So results and outcomes are not necessarily the same, right? Specifically, if you don't care the order in which something that's repetitive happens. Sometimes they will match up, but in this case, we don't care if the head happened the first, well, that's the last roll, or the middle roll, or the first roll. Okay, so those all count the same. Same thing for the 2s, and then, of course, there's only one way to get 3 heads. So we don't quite have, this is not a probability distribution. Okay, we're not quite there yet. When we combine all that and summarize our possible results, here's where we have the probability distribution table. Okay, we're going to summarize all those eight results and say how many of those total 0, how many total 1, 2, and 3. Okay, so I'm going to put up, I think both images are going to pop up here. I'm going to block this out so you focus in just on the probability distribution table. And we can see that, so here we have the number of heads. Okay, and then over here we have the number of number of results that produce that outcome. So we had 8 results, remember, only one of which gave us 0 heads. And so 1 out of 8 is the probability that would occur. Okay, and then we remember there's 3 out of the 8 give us 1 head, and so on. Now, again, these are going to equal 100%. And obviously, in this simple case, we're probably not going to forget about a set of results here. But in more complicated or more, something where you're not flipping coin, but you're trying to keep track of all the possible winners of a race, or all the possible, something more elaborate, we do need to be mindful and take some time to make sure that we're not forgetting certain outcomes. Okay, so all the graph over here is that we are putting that on a graph, right? Just like we built a bar chart out of a frequency or relative frequency table, here we have a probability distribution table. Let's put it on a graph. And we're just, the height of 3 here goes up to 1/8, right? Because that's our probability of that outcome. And the 2 goes all the way up to 3/8. You can, if you have nice clean fractions, you can leave them in the 1/8, 2/8, 3/8. Sometimes you'll see them as just, a decimal points, or if they're not clean fractions like that, you may just leave them as decimals. But this is a frequency distribution and or a probability distribution, and a good way to summarize the possible results of flipping 3 coins. And so much easier to interpret. Again, a lot of times this visual is better. Even just summarizing it in this table is helpful. Okay, so some other examples you can kind of work through, and I think we'll maybe just do the middle one here, but we could think about doing the same process with rolling 1 die or 2 die or a couple free throw attempts. Let's walk through rolling 2 dice and just the process in which we would maybe go about trying to build this. So let me click the right buttons. and connect here. Free advertising for that app. Sometimes I need to restart that, so that's maybe not a great advertisement for the app. We'll just hop back here while I click around on my computer. And so the first thing we would do is start with however many results we could have, right? So in the previous example, we had 8 different results. We had 2 times 2 times 2. Here, what do we have? Well, again, recalling from chapter 5, our simple equation here. Trying out a different color here. So we have m times n, right? There's only 2 things happening. We're rolling 2 dice. That's 6 times 6. Okay, so we have 36 results. Now we could write all these out, and we'll write some of them out. But you can see that pretty quickly with more complicated scenarios. We're going to need to kind of learn some mathematical shortcuts rather than writing all these out and counting up however many result in some outcome. So, but to get kind of the structure of what we're thinking here, we would just like with the coin flips, we want to lay out. So we'll have result, right? How many results we have. This would be that list of, we won't go through them all, but this would go on and on and on, all the way down towards the bottom here. We'd have 36, right? So there's 36 different different results that could occur. Now the important thing here again is to be mindful of what are the outcomes that we care about. And I think if we jump back, I think I listed consider the outcomes to be the sum of the 2 dice. So that's very different than if we care about the order or the specifics of each dice. So, we could have a 1 and a 1, but the outcome that we're interested in is really the sum, which is 2. And we could have a 1 and a 2, and that's going to produce a different sum, a different outcome. Now, these will continue to be different outcomes sometimes, but eventually, if we kind of got down the list of however we were organizing it, we would get a 2 and a 1, right? Probably like the 7th one that we come across, if we were ordering it this way. So that is going to give us a sum of 3 again, right? So a repeated outcome, much like we had repeated outcomes of flipping the coin. This 3 and this 3 are the same outcome, and so already we're seeing that that's going to have maybe 2 out of however many results. Okay, and there'd be more repeating here, so there'd be a 2 and a 2, so that's a 4. Somewhere down here there'd be a 3 and a 1, right? So now we have more 4s. Probably our last one, 6 and 6, right? Some more in between there, and we'd have a 12. Okay, but we see some repetition, and we could count up all of these and do the exact same thing we did with the coin flips. Okay, what did we do next with the coin flip? We actually built that probability distribution, right? This is kind of the work in the back. But what's the useful tool? Well, it's when we have it summarized, and we can say things like, here's the sums that we're interested in. I think that's on the screen. And what's the probability of that outcome? Okay, so again, we don't have 36 sums that we're interested in or outcomes that we're interested in. We only have it could be a 2, 3, 4 up to 12, and so we have 11 different outcomes. Okay, and we won't write them all down, but they'd be in there. And then what are we going to see? Well, there's only one way to get a 2, right? Or we can reference this table over here, or this big long list if we had it complete. And so we'd have one result can get us there. And how many results were there? Where there were 36. Okay, so 1 out of 36 times you're going to get a 2, or that's the likelihood. If you're going to roll a pair of die, you have a 1 in 36 chance, or a 1 in 36 likelihood of rolling a 2. Okay, this is going to feel familiar for Catan players out there. You know, that's why you don't build on the 2s. And so on. And so for the 3, we already saw there were 2, right? There you can have a 1 and a 2, a 2 and a 1. So you have a 2 out of 36. This becomes 3 out of 36. And again, for there, so somewhere in here there's a 7, and this 7 is 6 out of 36 if we were to go through and count them all up, and it'd come all the way back down to 1 out of 36 for a 12 in the way. But so if you know if you played enough Catan, you know that the most likely occurrence is moving the robber, right? So you're going to roll a 7 about a 6th of the time. Or if you play craps with your great grandfather, because those are the last people that played craps a lot, you'd also know more about that. Okay, so here, what we have here, and we skipped a few of these in the middle, but this is a probability distribution. And then often what we do is also visualize that and sketch it out on a graph, right? And so let's see if I might have enough room here. And so we'd have, this would be 2, 3, 4, 5. And each of these would have a height up to the probability of that outcome. Okay, so the 2 would go up just a bit to 1 out of 36. The 3 would go up to 2 out of 36, and so on. And so what we'd actually get, and the 12 would go up, and should finish this. We have lines, right? And so we get this actually pretty well. It's completely symmetrical, stepwise scenario here, where it looks like that. Okay, so there we have the probability distribution and kind of the graphical representation of that for 2 dice. And if you play a lot of Catan or Risk, or I don't know if people still play Risk, other dice-related games, you probably have kind of a working model of this in your head, or hopefully, because you'll do a lot better if you take this type of mentality as far as what's the likelihood of various outcomes. I think Catan, at least the original versions, gave you those little dots on the little circles to try to kind of give you a sense of this as you look at the board. Okay, so there we have building a probability distribution. So the next thing, so that's how we visualize and kind of summarize the probabilities. Let me jump back here. Get out of the way. Whoops. Okay. So just a little bit more about what variables we're talking about here, and what we mean by what is a random variable. So this is going to become important, that we are that we're working with a random variable, and that we're not pre-selecting what the outcome is. Now, so a random variable, again, we're talking about future events, or what might occur, the likelihood of the result or the outcome of an experiment. Now, that experiment, again, what we're saying is that by chance that there could be a different value, or there would be different values that might occur in this experiment. And so sometime, you make a pizza and your roommate eats three pieces. The next time she eats 4 or something. And so by kind of random chance, that outcome might vary by experiment. And what we're kind of assuming is that there is randomness to this, and that we don't know for certain, that she's going to eat 3 pieces this time. That's kind of silly because maybe you have a conversation and you know that ahead of time. But if you just were to make a pizza and leave it on the table, how many slices does she eat? So maybe some better examples. I think this one's from the book, but on a random or on a certain day shift on Monday, you have some employees that are absent. It's some value, some number. You're counting it up, but that number is random. You don't know for sure, but you might associate probabilities or be able to assign probabilities to what the chance is that it's 1 or 2 or 3. Same thing here. We have some the basketball team. The grade level of an individual can be considered a random variable. Again, it doesn't mean that they're equal chance, right? So I think in kind of popular language, we sometimes think of random as in place of equal probabilities. So rolling a single die, right? And that's an equal chance. But as we just saw, we're rolling 2 dice and the outcomes are not equal chances, right? So there are certain outcomes which we assign a higher probability than other ones. So for instance, the varsity girls basketball team, we probably would assign a higher likelihood of the varsity players being maybe juniors and seniors than freshmen or sophomore. Okay, so other examples, I think that's one I was just referring to, pieces of pizza. We could think about the amount of cloud cover, or the percentage of cloud cover at noon, so 13 minutes ago. That would be more continuous, right? So we could have the 63.4% chance, but that's still a random variable. Another more pressing random variable is what are the new number of new COVID cases in Wisconsin on a particular day. Again, that's random. We don't know what it's going to be. We can associate probabilities with different numbers, but each day that's kind of a random experiment, and everything about it isn't necessarily random. There's causes as to why a certain outcome would happen, but we don't know specifically what that's going to be. And then again, to just drive home, some of those are discrete and some are continuous. Again, the idea of discrete being those clearly separated values. So it's either, if you restrict it to be how many pizza slices does she eat, it's either 1, 2, 3. I guess you could consider, she ate 2.3, but that's only really relevant if you're going to then save the 0.7 slice of pizza and eat it later. I guess maybe in college that's a thing. But if we count that as she's eaten the 3rd pizza slice because she's slobbered on it, then that counts as a full value. So often discrete variables are a result of counting. It's you count up a number, and that's going to indicate that you're probably dealing in discrete. We went through the coin flipping. Your book walks through an example of credit cards carried by a group of customers, and actually here's the probability distribution. So again, and this is a good one to highlight because so far we've had a nice kind of a nice pyramid shape, right? So there were equal chances of 0 or 3 heads, and then there were 1 and 2 had an equal chance in the middle. Our 2 dice roll was nice and up and down, but this is not, right? This is probably taken from empirical data, right? So how do we learn about probabilities? So far we've been looking at them kind of classical probabilities, so coin flips, rolling of dice. We have ways to assign likelihoods based on just the mathematical logic, but we said other ways of assigning probabilities, right, when we started talking about this in chapter 5, is oftentimes we rely on empirical data. So we may have found we may have a bunch of information about other customers and how many credit cards they carry in their wallet, now if we turn and talk about, maybe a future customer or a random customer within that group, we would then have a way to build these likelihoods, and they're not these nice symmetrical pictures. In fact, they kind of jump around and whatnot. So probability distributions can look all kinds of different crazy ways. They don't have to be those nice clean cut scenarios. So foreshadowing chapter 7, when we get into continuous variables, again here, this is any value along the way can be the result, right? And so measuring, and I know I used flour as a certain cup amount. That's more for the recipe, but if you wanted to, how much flour do I have here, and you weighed it, you could have 356 grams or 357.2 grams and so on. Time, we usually can distinguish time very in between any value. Snowfall or rainfall, it's a pretty classic example. And so that's just to say we need to be mindful as we look at what experiment we're dealing with, right? And so largely that's where this decision comes down, because we could be interested in the experiment of snowfall. We just may not be able to summarize it with our tools in chapter 6. We'll need to turn to the tools in chapter 7 because of the way that the outcomes occur. Okay, so we'll just touch a little bit on this here today. And then I want to just highlight what kind of the rest of chapter 6 talks about. So, but we've done the frequency, kind of the frequency table, which we now call basically a probability distribution. We've built that, and then we visualized it with basically the equivalent of a bar chart, right? We're just plotting that data on the graph. The other two big things is we want to be able to take into account the mean, or calculate the mean, and the standard deviation or the variance. Right, they're one and the same. It's just the same thing. It's just the square root to change back to the standard deviation. So we can do the same thing here, and again, same concept. We're representing the central location of this data, but in probability, we often refer to it as what's called the expected value. The expected value is just the mean result, or the center of our expectations. It's what we expect on average to have occurred. And so I've put the equation up here, and it looks a little different. And I think I maybe warned us of this earlier today, but the mean, it doesn't look exactly like our typical mu is equal to the sum of x divided by n. But if you recall back to our sum of the grouped data, this is almost exactly like that if we think of the probabilities of being a fraction. Okay, and so in a video, I'll kind of work through both at the same time, and you can see that they basically are doing the same thing. But really what we're doing is adding up all those x's and multiplying by the chance that x occurs. And so it's the same concept. It's what we can expect to have happened. Yeah. And expected value has a pretty powerful place in decision making. Businesses spend a lot of time thinking about expected value of a certain activity, right? So if you want to expand, expand into a new, I don't know who's expanding in this economy, but if you wanted to expand into open up a new plant, there's various outcomes that might occur, right? So that might go really well for you and you make $1 million, or it might go okay and you earn $500,000. We'd want to associate some percentages there. And then once we do that, we can calculate kind of an expected value. How much should we value this opportunity? Maybe there's a 10% chance that you lose $1 million. So how do we factor all that in? Well, we can build an expected value if we know, or if we have a good feel of the probabilities associated with all of these different outcomes. We can summarize that and say, okay, the expected value is 400,000 for this opportunity to expand. Okay, so and then we will also calculate the spread or the variation. Again, looks a little different, but note, I think it'll be easier if I just write it here. So we're talking the variance as being the sum of the deviation squared, and then we also are doing this times p of x, right? And so while that looks a little different, I guess we sum up after. Okay, so I just want to highlight that this is all built off of the same concept, right? So we're returning to this idea of deviations from the mean. We just built the mean. Again, in it's going to look slightly different. Sum of x p of x. Whoop. Okay, but this p of x comes within both equations, and it'll feel natural after you work through it a few times. So what I want to highlight here, as you go into reading into the chapter and watching some videos and starting to work on the Connect assignment, this is a slightly different way to organize it, but it's based on the same principles. Okay, so we're still going to calculate the deviations, square those deviations, and then instead of directly adding them up and dividing by n, we are multiplying each of those by the likelihood in which they occur. Right? The deviation squared, how likely is that deviation squared to occur? This is all going to sum to 1, or all those probabilities do. And so it's very similar to that grouped standard deviation calculation of a few chapters ago. Okay, so that's kind of the middle task of chapter 6. And then towards the end of chapter 6, I don't know if I have these quite in order. I just want to touch on so two things that we cover, the binomial distribution, and the math is a little different here. In fact, you could do the same cumbersome math for binomial, but there's actually kind of shortcuts here, because binomial distribution is just it's one of two outcomes, right? So a binomial experiment, it's either yes or no. It's either you made the free throw or you missed the free throw. You survived or you died. So it's a true or false, right? It's one of two outcomes. So by the bi being the functional term there. And so that leads us to a little different math. And in fact, they're easier to calculate. And so that's why we specifically turn to them. And they also occur quite often. So a lot of stuff can be considered a yes or no, or a true or false, right? We talked how prevalent dummy variables are when we were dealing with data, in that if you can make them 1 or 0, on or off, not only is it pretty handy with a computer, but they occur not infrequently. And so the fact that the math is pretty simple is helpful as well. So we'll spend some time specifically talking about that. It's a unique situation, but it's common enough. And as I point out here, even things that have multiple outcomes, right? So you roll a die, it's one of 6 outcomes, but sometimes, especially if you're playing a game, like let's say you're playing Risk, if you still know what that is, you need to roll at least some value, right? Or if I'm really going to set you if I say you're playing D&D, but you need to roll a 16 up to a 20 to slay the goblin. That you can consider that as either yes, you rolled that high, or no, you didn't, right? So the possible outcomes can be distinguished into a yes or no. And so that's why I say it's so prevalent, is that even in cases where there's multiple outcomes, we can often describe them, or we're often interested in just whether or not you made it past some value, some level, or you didn't. Was the person discharged from the hospital or not, or was their oxygen 92 or above, or not. You either win the lottery or you don't. Prevalent example: get the disease or you don't get it. And of course, sometimes it's more important as to level of, again, rambling on about COVID, but it's not always just if you got the disease or not, but how critical. But if we are interested in yes, no, we can use binomial distributions. And so the language of this that we often use in statistics is success versus failure. So if you're considering it heads is a success, tails a failure, we often just talk about successes and failures. So there's a little bit of different math, and we'll cover this more on Friday and in some videos as to how we go about that. It uses the combination formula. So here's that C that we covered in chapter 5. So we have that, but we also add in this this other part. So we'll talk more about that, not to get into the weeds now. So we have binomial distributions, and then lastly, we will touch briefly on hypergeometric distributions, which is, again, just a kind of a unique case, but you can think of it as sort of frame it for your thinking. It's kind of in the line of, remember in chapter 5, we wanted to be clear about whether the probabilities were conditional or not. So in the hypergeometric distribution, we can think of that as kind of conditional probabilities, in that there's kind of it's very similar to, we pulled the green marble out and that impacts the likelihood of pulling another green marble. That's where we're at with the hypergeometric. It's kind of an offshoot of binomial, and based around the conditionality. So so sometimes, so apologies for that. The video that I post will be clearer. I'm losing Zoom. It's getting fuzzy, but the probability for that binomial, again, as I was saying, is pretty gross looking, but notice it has that combination formula. So Andrew asked to just see this written out, and we'll I'm in the way, I'll move myself too. So we have that combination formula at the start around the C, and then the pi's there. That's in probability statistics, we use pi to indicate like the likelihood of a success. So here, if you're thinking about a free throw shooter, you could think of that as being 0.7, and that's what we would be plugging in. So we'll talk more about the specifics of each of those variables there, or parameters. Know that we've started along the course, at least, of understanding that, right? So the combinations formula, we've built that tool in chapter 5 to help us out now as we move forward. Okay, so that was a lot of information, and not a ton of examples. So I realize that I know that you're probably anxious to see it in practice, and so I will be posting videos in the next day or so of walking through some of these and some of these more specifics. But then on Friday we'll come back and we'll hack through some of these binomial probabilities and things like that. Let me know if you have questions. Again, office hours, feel free to swing in to those. Just to reiterate, if I'm not in the Zoom room, I'm probably sitting right here just without the program open, and I usually get a little notification, so I'll probably pop on. If I don't, shoot me an email and I'll for sure make sure I pull this up. So with that said, we'll leave it there, and good to virtually be with y'all.